Paragraph 58. Certain crystals of tourmaline and of other minerals possess what may be called electric polarity. Suppose a crystal of tourmaline to be at a uniform temperature and apparently free from electrification on its surface. Let its temperature be now raised, the crystal remaining insulated. One end will be found positively and the other end negatively electrified. Let the surface be deprived of this apparent electrification by means of a flame or otherwise. Then, if the crystal be made still hotter, electrification of the same kind as before will appear. But if the crystal be cooled, the end which was positive when the crystal was heated will become negative. These electrifications are observed at the extremities of the crystallographic axis. Some crystals are terminated by a six-sided pyramid at one end and by a three-sided pyramid at the other. In these, the end having the six-sided pyramid becomes positive when the crystal is heated. Sir William Thomson supposes every portion of these and other hemihedral crystals to have a definite electric polarity, the intensity of which depends on the temperature. When the surface is passed through a flame, every part of the surface becomes electrified to such an extent as to exactly neutralize for all external points the effect of the internal polarity. The crystal then has no external electrical action, nor any tendency to change its mode of electrification. But if it be heated or cooled, the interior polarization of each particle of the crystal is altered and can no longer be balanced by the superficial electrification, so that there is a resultant external action. Plan of this treatise. Paragraph 59. In the following treatise, I propose first to explain the ordinary theory of electrical action, which considers it as depending only on the electrified bodies and on their relative position, without taking account of any phenomena which may take place in the surrounding media. In this way, we shall establish the law of inverse square, the theory of the potential, and the equations of Laplace and Poisson. We shall next consider the charges and potentials of a system of electrified conductors as connected by a system of equations, the coefficients of which may be supposed to be determined by experiment in those cases in which our present mathematical methods are not applicable. And from these, we shall determine the mechanical forces acting between the different electrified bodies. We shall then investigate certain general theorems by which Green, Gauss, and Thomson have indicated that the conditions of equilibrium of the distribution of electricity. One result of these investigations is that if Poisson's equation is satisfied by any function, and if at the surface of every conductor the function has the value of the potential of that conductor, then the function expresses the actual potential of the system at every point. We also deduce a method of finding problems capable of exact solution. In Thomson's theorem, the total energy of the system is expressed in the form of the integral of a certain quantity extended over the whole space between the electrified bodies, and also in the form of an integral extended over the electrified surfaces only. The equation between these two expressions may be thus interpreted physically. We may conceive the relation into which the electrified bodies are thrown, either as the result of the state of the intervening medium, or as the result of a direct action between the electrified bodies at a distance. If we adopt the latter conception, we may determine the law of the action, but we can go no further in speculating on its cause. If, on the other hand, we adopt the conception of action through a medium, we are led to inquire into the nature of that action in each part of the medium. It appears from the theorem that if we are to look for the seat of the electric energy in the different parts of the dielectric medium, the amount of energy in any small part must depend on the square of the intensity of the resultant electromotive force at that place, multiplied by a coefficient called the specific inductive capacity of the medium. It is better, however, in considering the theory of dielectrics in the most general point of view, to distinguish between the electromotive force at any point and the electric polarization of the medium at that point, since these directed quantities, though related to one another, are not in some solid substances in the same direction. The most general expression for the electric energy of the medium per unit of volume is half the product of the electromotive force and the electric polarization multiplied by the cosine of the angle between their directions. In all fluid dielectrics, the electromotive force and the electric polarization are in the same direction and in a constant ratio. If we calculate on this hypothesis the total energy residing in the medium, we shall find it equal to the energy due to the electrification of the conductors on the hypothesis of direct action at a distance. Hence, the two hypotheses are mathematically equivalent. If we now proceed to investigate the mechanical state of the medium on the hypothesis that the mechanical action observed between electrified bodies is exerted through and by means of the medium, as in the familiar instances of the action of one body on another by means of the tension of a rope or the pressure of a rod, we find that the medium must be in a state of mechanical stress. The nature of this stress is, as Faraday pointed out, a tension along the lines of force combined with an equal pressure in all directions at right angles to these lines. The magnitude of these stresses is proportional to the energy of the electrification, or, in other words, to the square of the resultant electromotive force, multiplied by the specific inductive capacity of the medium. This distribution of stress is the only one consistent with the observed mechanical action on the electrified bodies, and also with the observed equilibrium of the fluid dielectric which surrounds them. I have therefore thought it a warrantable step in scientific procedure to assume the actual existence of this state of stress and to follow the assumption into its consequences. Finding the phrase electric tension used in several vague senses, I have attempted to confine it to what I conceive to have been in the mind of some of those who have used it, namely, the state of stress in the dielectric medium which causes motion of the electrified bodies and leads, when continually augmented, to disruptive discharge. Electric tension, in this sense, is a tension of exactly the same kind, and measured in the same way, as the tension of a rope, and the dielectric medium, which can support a certain tension and no more, may be said to have a certain strength in exactly the same sense as the rope is said to have a certain strength. Thus, for example, Thomson has found that air at the ordinary pressure and temperature can support an electric tension of 9,600 grams weight per square foot before a spark passes. Paragraph 60. From the hypothesis that electric action is not a direct action between bodies at a distance, but is exerted by means of the medium between the bodies, we have deduced that this medium is in the state of stress. We have also ascertained the character of the stress and compared it with the stresses which may exist in other or in solid bodies. Along the lines of force, there is tension, and perpendicular to them there is pressure, the numerical magnitude of these stresses being equal, and each proportional to the square of the resultant electromotive force multiplied by the specific inductive capacity of the medium. In this way, we obtain an idea of the nature of the electric polarization of the dielectric medium. An elementary portion of a body may be said to be polarized when it acquires equal and opposite properties on two opposite sides. The idea of internal polarity may be studied to the greatest advantage as exemplified in permanent magnets, and it will be explained at greater length when we come to treat of magnetism. The electric polarization of an elementary portion of a dielectric is a forced state into which the medium is thrown by the action of electromotive force, and which disappears when that force is removed. We may conceive it to consist in what we may call an electrical displacement produced by the electromotive force. When the electromotive force acts on a conducting medium, it produces a current through it. But if the medium is a non-conductor or dielectric, the current cannot flow through the medium, but the electricity is displaced within the medium in the direction of the electromotive force. The extent of this displacement depending on the magnitude of the electromotive force, so that if the electromotive force increases or diminishes, the electric displacement increases and diminishes in the same ratio. The amount of the displacement is measured by the quantity of electricity which crosses unit of area, while the displacement increases from 0 to its actual amount. This, therefore, is the measure of the electric polarization. The analogy between the action of electromotive force in producing electric displacement and of ordinary mechanical force in producing the displacement of an elastic body is so obvious that I have ventured to call the ratio of the electromotive force to the corresponding electric displacement the coefficient of electric elasticity of the medium. This coefficient is different in different media and varies inversely as the specific inductive capacity of each medium. The variations of electric displacement evidently constitute electric currents. These currents, however, can only exist during the variation of the displacement, and therefore, since the displacement cannot exceed a certain value without causing disruptive discharge, they cannot be continued indefinitely in the same direction, like the currents through conductors. In tourmaline and other pyroelectric crystals, it is probable that a state of electric polarization exists, which depends upon temperature and does not require an external electromotive force to produce it. If the interior of a body were in a state of permanent electric polarization, the outside would gradually become charged in such a manner as to neutralize the action of the internal electrification for all points outside the body. This external superficial charge could not be detected by any of the ordinary tests and could not be removed by any of the ordinary methods for discharging superficial electrification. The internal polarization of the substance would therefore never be discovered unless by some means, such as change of temperature, the amount of the internal polarization could be increased or diminished. The external electrification would then be no longer capable of neutralizing the external effect of the internal polarization, and an apparent electrification would be observed, as in the case of tourmaline. If a charge is uniformly distributed over the surface of a sphere, the resultant force at any point of the medium surrounding the sphere is numerically equal to the charge divided by the square of the distance from the center of the sphere. This resultant force, according to our theory, is accompanied by a displacement of electricity in a direction outwards from the sphere. If we now draw a concentric spherical surface of radius r, the whole displacement, call it E sub s, through this surface will be proportional to the resultant force multiplied by the area of the spherical surface. But the resultant force is directly as the charge and inversely as the square of the radius, while the area of the surface is directly as the square of the radius. Hence, the whole displacement, E sub s, is proportional to the charge and is independent of the radius. To determine the ratio between the charge E and the quantity of electricity E displaced outwards through the spherical surface, let us consider the work done upon the medium in the region between two concentric spherical surfaces, while the displacement is increased from E to E plus delta E. If V1 and V2 denote the potentials at the inner and the outer of these surfaces respectively, the electromotive force by which the additional displacement is produced is V1 minus V2, so that the work spent in augmenting the displacement is the difference of V1 and V2 multiplied by delta E. If we now make the inner surface coincide with that of the electrified sphere and make the radius of the other infinite, V1 becomes V, the potential of the sphere, and V2 becomes 0, so that the whole work done in the surrounding medium is V delta E. But by the ordinary theory, the work done in augmenting the charge is V delta E, and if this is spent, as we suppose, in augmenting the displacement, delta E equals delta E, and since E and E vanish together, E equals E. Or the displacement outwards through any spherical surface concentric with the sphere is equal to the charge on the sphere. To fix our ideas of electric displacement, let us consider an accumulator formed of two conducting plates A and B separated by a stratum of a dielectric C. Let W be a conducting wire joining A and B, and let us suppose that by the action of an electromotive force, a quantity Q of positive electricity is transferred along the wire from B to A. The positive electrification of A and the negative electrification of B will produce a certain electromotive force acting from A towards B in the dielectric stratum, and this will produce an electric displacement from A towards B within the dielectric. The amount of this displacement, as measured by the quantity of electricity forced across an imaginary section of the dielectric, dividing it into two strata, will be, according to our theory, exactly Q. It appears, therefore, that at the same time that a quantity Q of electricity is being transferred along the wire by the electromotive force from B towards A, so as to cross every section of the wire, the same quantity of electricity crosses every section of the dielectric from A towards B by reason of the electric displacement. The reverse motions of electricity will take place during the discharge of the accumulator. In the wire, the discharge will be Q from A to B, And in the dielectric, the displacement will subside, and a quantity of electricity Q will cross every section from B towards A. Every case of electrification or discharge may therefore be considered as a motion in a closed circuit, such that at every section of the circuit, the same quantity of electricity crosses in the same time. And this is use case not only in the voltaic circuit where it has always been recognized, but in those cases in which electricity has been generally supposed to be accumulated in certain places. Paragraph 61. We are thus led to a very remarkable consequence of the theory which we are examining, namely that the quantities of electricity are like those of an incompressible fluid, so that the total quantity within an imaginary fixed closed surface remains always the same. This appearance has at first sight direct inconvenience to the fact that we can charge a conductor and then introduce it into the closed space, and so alter the quantity of electricity within that space. But we must remember that the ordinary theory takes no account of the electric displacement in the substance of dielectrics, which we have been investigating, but confines its attention to the electrification at the bounding surfaces of the conductors and dielectrics. In the case of the charged conductor, let us suppose the charge to be positive. Then, if the surrounding dielectric extends on all sides beyond the closed surface, there will be electric polarization, accompanied with displacement from within outwards all over the closed surface, and the surface integral of the displacement taken over the surface will be equal to the charge on the conductor within. Thus, when the charged conductor is introduced into the closed space, there is immediately a displacement of a quantity of electricity equal to the charge through the surface from within outwards, and the whole quantity within the surface remains the same. The theory of electric polarization will be discussed at greater length in Chapter 5, and a mechanical illustration of it will be given in Article 334. But its importance cannot be fully understood till we arrive at the study of electromagnetic phenomena. Paragraph 62. The peculiar features of the theory as we have now developed them are, first, that the energy of electrification resides in the dielectric medium, whether that medium be solid, liquid, or gaseous, dense or rare, or even deprived of ordinary gross matter, provided it be still capable of transmitting electrical action. Second, that the energy in any part of the medium is stored up in the form of a state of constraint called electric polarization, the amount of which depends on the resultant electromotive force at the place. Third, the electromotive force acting on a dielectric produces what we have called electric displacement, the relation between the force and the displacement being, in the most general case, of a kind to be afterwards investigated in treating of conduction, but in the most important cases, the force is in the same direction as the displacement and is numerically equal to the displacement multiplied by a quantity which we have called the coefficient of electric elasticity of the dielectric. Fourth, that the energy per unit of volume of the dielectric arising from the electric polarization is half the product of the electromotive force and the electric displacement multiplied, if necessary, by the cosine of the angle between their directions. Fifth, that in fluid dielectrics, the electric polarization is accompanied by a tension in the direction of the lines of force, combined with an equal pressure in all directions at right angles to the lines of force, the amount of the tension or pressure per unit of area being numerically equal to the energy per unit of volume at the same place. Sixth, that the surfaces of any elementary portion into which we may conceive the volume of the dielectric divided must be conceived to be electrified, so that the surface density at any point of the surface is equal in magnitude to the displacement through that point of the surface reckoned inwards, so that if the displacement is in the positive direction, the surface of the element will be electrified negatively on the positive side and positively on the negative side. These superficial electrifications will in general destroy one another when consecutive elements are considered, except where the dielectric has an internal charge or at the surface of the dielectric. Seventh, that whatever electricity may be, and whatever we may understand by the movement of electricity, the phenomenon which we have called electric displacement is a movement of electricity in the same sense as the transference of a definite quantity of electricity through a wire is a movement of electricity, the only difference being that in the dielectric there is a force which we have called electric elasticity, which acts against the electric displacement and forces the electricity back when the electromotive force is removed. Whereas in the conducting wire, the electric elasticity is continually giving way so that a current of true conduction is set up, and the resistance depends not on the total quantity of electricity displaced from its position of equilibrium, but on the quantity which crosses a section of the conductor in a given time. Eighth, that in every case the motion of electricity is subject to the same condition as that of an incompressible fluid, namely, that at every instant as much must flow out of any given closed space as flows into it. It follows from this that every electric current must form a closed circuit. The importance of this result will be seen when we investigate the laws of electromagnetism. Since, as we have shown, the theory of direct action at a distance is mathematically identical with that of action by means of a medium, the actual phenomena may be explained by the one theory as well as by the other, provided suitable hypotheses be introduced when any difficulty occurs. Thus, Masadi has deduced the mathematical theory of dielectrics from the ordinary theory of attraction by merely giving an electric instead of a magnetic interpretation to the symbols in the investigation by which Poisson has deduced the theory of magnetic induction from the theory of magnetic fluids. He assumes the existence within the dielectric of small conducting elements capable of having their opposite surfaces oppositely electrified by induction, but not capable of losing or gaining electricity on the whole, owing to their being insulated from each other by a non-conducting medium. This theory of dielectrics is consistent with the laws of electricity and may be actually true. If it is true, the specific inductive capacity of a dielectric may be greater, but cannot be less than that of air or vacuum. No instance has yet been found of a dielectric having an inductive capacity less than that of air, but if such should be discovered, Mosadde's theory must be abandoned, although his formula would all remain exact and would only require us to alter the sign of a coefficient. In the theory which I propose to develop, the mathematical methods are founded upon the smallest possible amount of hypothesis, and thus equations of the same form are found applicable to phenomena which are certainly of quite different natures, as for instance, electric induction through dielectrics, conduction through conductors, and magnetic induction. In all these cases, the relation between the force and the effect produced is expressed by a set of equations of the same kind, so that when a problem in one of these subjects is solved, the problem and its solution may be translated into the language of the other subjects, and the results in their new form will also be true.